In this part of the lecture, I will talk about the diene and polyene metal complexes. If you look at the total ligand map, you find that we have discussed mostly the one carbon ligands, and then we proceeded to go down in this map and we talked about alkenes and then alkynes. The next logical thing would be, in one sense, to talk about allyl complexes, the three carbon framework. But instead, we will talk about the dienes because logically or conceptually they are simpler to discuss and more related to the alkenes. So let's talk about dienes today, and then we'll talk about trienes later. So basically what we are doing is that we are grouping the even number of carbon atoms, the ligands which contain the even number of carbon atoms together. So we want to look at them together. So today we will start with the diene. Butadiene is the simplest example of this group of ligands. I have for you pictured on the top of this slide the molecular orbitals of butadiene, Psi1, Psi2, Psi3, and Psi4. That is, only the pi molecular orbitals are described here. You will notice that the lowest energy molecular orbital has got all the phases in the same fashion, which means that there is no node as you progress from C1 to C4. Psi2, on the other hand, has got one node, and that node could be drawn here, right here. That is a node. And when it comes to Psi3, you find that there are two nodes right here, these two nodes. And then for Psi4, you have three nodes. If you look at metal orbitals, it's convenient to just draw them out in terms of Nd, n plus 1 s, and n plus 1 p orbitals. You might want to draw this in this particular fashion because it tells you the type of interactions these orbitals are going to have with the butadiene. I have drawn them in that particular fashion. The y-axis is along the width of the screen, is parallel to the width of the screen, and the z-axis is parallel to the height of the screen. So the height is along the z-axis and the width is along the y-axis. X-axis in this particular notation, the way I've drawn it, is perpendicular to the screen. Mainly you're looking through the x-axis at the ligand and the metal orbital. So these ligands now match up, these orbitals on the metal now match up with the ligand orbitals. You find that the interactions are in this particular fashion. First, you have sigma interactions. The lowest energy ligand Psi1 interacts with either the pz or the dz squared or the s. All of them could be empty. Especially the p and the s are n plus 1 orbitals. If the metal is from a 3D row, then 4s and 4p orbitals are empty. So these are orbitals that are going to accept electron density from the ligand onto the metal. So Psi1 is a filled orbital. That's the lowest energy orbital that is filled, and so is Psi2. So Psi1 will now pump in electron density into the lowest energy orbital on the metal. And very often it is going to be the dz squared orbital. And this has got very good overlap. If you keep it in the center at this position, then the metal will have very good overlap with the ligand orbitals. On the other hand, the Psi2 orbital, which has got a single node, will match with the py orbital, which has also got a single node. And you'll notice that if I position the metal in this place, that is right in the center of the 4 carbon atoms, below the plane of the 4 carbon atoms, then the py will match perfectly with the psi2 orbital, and similarly the dyz also can interact with the psi2 orbital. If the dyz is filled, then these two interactions, the interaction of psi2 with dyz, will become repulsive because both will be filled orbitals. But very often these two orbitals are perfectly matched in terms of symmetry, energy, and in terms of the occupancy to form a nice bonding orbital. So these two will form a nice bonding combination, and these two orbitals on the metal, the py and the psi2, will also form a nice bonding combination. Now you look at psi3. Psi3 is the one which had two nodes right here. There's one node here and there's one node here. And so these two orbitals are arranged in such a way that they can interact with the px orbital. Now, remember, the px is not going to be a filled orbital. That's a high energy p orbital which is going to be empty. On the other hand, if the dxz orbital has got a bunch of electrons, then it can pump in electron density into the empty psi3 orbital. Psi3 is going to be empty and psi4 is also going to be empty. You will notice that the dxz is in fact perfectly poised. If you place the metal in the same position as we mentioned earlier in the center, below the plane of the 4 carbon atoms, then the dxz orbital will have good overlap with this pi orbital which is present here. These two interactions are in fact pi interactions. The interaction with a pi interaction if it loses the overlap when you rotate the metal with respect to the ligand. On the other hand, this is a sigma interaction because if you rotate the metal with respect to the ligand, there is no loss of overlap. So these two orbitals will lose overlap when you rotate them by 45 degrees or 90 degrees. If you rotate them by 180 degrees, they'll come back to another combination which can form a bonding combination. Now, when you come to the fourth molecular orbital on the butadiene, this is the one which has 3 nodes. This is the one which has 3 nodes, and you will notice that the dxy has got the right symmetry to interact with the psi4 orbital. And in case the dxy is filled and we know that the psi4 is empty, if the dxy is filled, then this can form a bonding combination also. But this particular bonding combination is in fact a delta overlap. What is the meaning of a delta overlap? The delta overlap is something that is going to lose overlap when you rotate it. By 90 degrees, it will come to a perfectly opposite configuration. If you rotate it by 45 degrees, you will lose overlap completely. And so the delta overlap is one where if you rotate it by even 45 degrees, you will lose overlap and it will become 0. And if you rotate it by 90 degrees, you will come to an alternate configuration which can be combined by putting a minus sign. So you can check this out for yourself. So these metal orbitals are all going to interact with the ligand orbitals, or at least they have a suitable combination. The tx squared minus y squared, on the other hand, does not have a combination to interact with. So that is one orbital which has been left out. And that orbital, whether it's filled or empty, it doesn't matter. Because of symmetry, it doesn't have a right combination. So this is an actual calculation. Up to now, I had put up for you some schematic representations of the four molecular orbitals. These are the same molecular orbitals, but this time this is coming out of a computational study. And you can see that the coefficients of these four carbon atoms, the coefficients of the four carbon atom p orbitals are not the same in the four molecular orbitals. Although the phases are similar to what I had shown you, the sizes are not exactly the same. Before we proceed further, I want to discuss with you one more aspect, and that is the aspect of energy of the molecular orbitals. If you look at the ethylene molecule, the bonding orbital is at minus 7.6 electron volts, and the antibonding orbital is at minus 0.1 electron volt. The gap between the two orbitals is minus 7.5 electron volts. You can just say that the gap is 7.5 electron volts. There doesn't have to be a minus sign. When you take the butadiene in the cis form, the bonding orbital is at minus 6.7. This is the side 2. The side 2 orbital is at minus 6.7 electron volts. On the other hand, the lowest unoccupied molecular orbital is at minus 0.9. Notice how the antibonding orbital or the lowest unoccupied orbital has come down in energy for cis butadiene. So butadiene is going to be a better acceptor of electron density compared to ethylene. In the same fashion, if you look at the donor orbitals of butadiene, you will notice that side 2 is going to be a better donor than ethylene itself. Okay, so the energy levels of the butadiene molecule suggests that there will be better interaction between a metal. If it is the same metal, for example, there will be better interaction between the metal and the butadiene, both in terms of donation and back donation. These interactions are going to be better. Why? There is lower energy of the LUMO and higher energy of the HOMO. So the higher the energy of the HOMO, remember minus 6.7 is higher than minus 7.6. Minus 7.6 suggests that it is held tightly by the nucleus. Minus 6.7 is at a higher energy level. So the higher the HOMO, the better the donation capability. The lower the LUMO, the better the acceptor ability. So butadiene compared to ethylene, electronically it is going to be a better donor and a better acceptor. So I have noted the same points here. This time, of course, I have drawn for you the actual molecular orbitals. But notice that butadiene, although we have indicated it as a flat molecule, when you try to optimize it, you try to find the best geometry of cis butadiene, it doesn't like to be flat. And that is because what happens is the two hydrogens are close enough for interaction. And so they are too close for comfort and they move apart from each other slightly by twisting around the sigma bond. Now let me introduce you to the concept of bond orders. Bond order is something that you're already familiar with from your earlier courses, but I want to discuss it a little more quantitatively in these complexes. And so I want you to see that there is an empirical relationship between the bond distance and the bond order. And that is not surprising. If you take a single carbon-carbon bond as in ethane or in diamond, the distance is around 1.54 angstroms or 154 picometers. If you take ethylene, the bond distance is 134 picometers. And if you go to acetylene, the distance comes down almost to 120 picometers. So you can see that as the bond order goes up, the bond distance goes down. And you can now relate the carbon-carbon bond distance that is observed to an empirical relationship to the fractional pi bond order between the two carbon atoms. So in other words, if you have a observed carbon-carbon bond distance of 120 picometers, then you can relate it to the single bond distance, approximate single bond distance, minus the pi bond order. If you increase the pi bond order, the bond distance is going to decrease. If you take free butadiene, what you notice is that the bond distance between the first two carbons, C1 and C2, is 134 picometers. And this is very close to the bond distance that is observed in ethylene. On the other hand, if I go to C2, C3 distance, the distance is 148 picometers. Clearly, that distance suggests that it is shorter than what is observed in ethane, and at the same time, it is longer than what is observed for ethylene. Now let's take a look at the bond distances which are present in the butadiene FeCO3 molecule. Notice that this molecule was synthesized as early as 1938. It was synthesized as early as 1938, and of course the crystallographic structure was characterized much later. But if you look at the carbon-carbon bond distances in this molecule, it turns out to be very similar for C1C2 and C2C3. This is in fact indicative of the changes in bond order as a function of the coordination of the iron tricarbonyl moiety. When the iron tricarbonyl is bound to the butadiene, the bond orders change from what is observed in free butadiene to what is observed in the complex. And if you solve for the bond distance between the two carbons, that is C2 and C3, you notice that the bond order is actually increased to 1.59. I will now refer you to the three-dimensional structure of butadiene and tricarbonyl. This is available in your team's website. You should be able to go there and link on the and double click on the zip file to examine the structure, the three-dimensional structure of the butadiene complex. I now want to introduce you to what is happening in the first excited state of butadiene. In the ground state of butadiene, Psi1 and Psi2 are filled with 2 electrons each, and the bond distance is 1.36 and 1.45 between the central carbon atoms. When you photoexcite the molecule, you push 1 electron from Psi2 to Psi3, and the bond distance between C2 and C3 actually decreases. This decrease in bond distance, of course, goes with an increase in the pi bond order. And you might be wondering, why is it that this bond distance is becoming short? If you look at the nature of Psi3, you realize that Psi2 and Psi3 actually has got no node between C2 and C3. So as a result, population of Psi3 results in the shortening of the bond between C2 and C3. Keep this in mind, and then we will look at the butadiene iron tricarbonyl complex. So here is the butadiene iron tricarbonyl complex. What we have noted is that the bond distance between the C1 and C2 has now become longer. This should not come as a surprise because we are removing electron density from this bond and pushing it into the empty orbitals of iron. And what we are doing, according to the DCD model that we tried to develop in the first few slides of this lecture, we are populating the Psi3 molecular orbital. Population of Psi3 molecular orbital results in a bonding situation between C2 and C3. And so this bond actually becomes shorter. It was 1.469 in the free butadiene, or 1.47, and it has become 1.414. Notice that the same situation was observed, a similar situation was encountered in the photoexcitation of butadiene. So, complexation of iron tricarbonyl moiety to butadiene results in a situation which is very similar to photoexcitation of free butadiene. So let me conclude this discussion of bonding in butadiene with metal carbonyls or metal atoms in complexes by showing you the picture which I showed you earlier. Basically, what is happening is that Psi1, which has got a pi bond order, which has got no nodes between the carbons in the 4 carbon atoms of butadiene, that molecular orbital is pushing electron density into the empty orbitals of the metal. This results in reduction of bond order between C1 and C2 and C3 and C4. It results in reduction of bond order between C1 and C2 and C3 and C4 primarily. The second thing that happens is the electron density that is pumped into Psi3 populates a molecular orbital which has got a bonding combination of C2 and C3. The p orbitals of C2 and C3 are having a bonding combination. As a result, the bond between C2 and C3 are strengthened as a result of electron density being pushed into Psi3. So removal of electron density from Psi1 and Psi2 reduces the pi bond order between the carbons, especially between carbon atoms C2 and C3. The population of this molecular orbital Psi1 has the effect of having partial double bond between C2 and C3. When you remove electron density from Psi1, this bond length between C2 and C3 is going to increase. But population of Psi3, on the other hand, that is going to improve the bond distance between C2 and C3. So there's going to be a balance of these two effects, and it is very clear from looking at the bond distances that there is significant amount of electron density removed from Psi1 and Psi2 and pumped into Psi3, because population of Psi3 is the one which is causing the bond distance between C2 and C3 to decrease. Clearly C2 and C3 have short bond lengths. We'll see that in one other complex now. And the second thing we notice is that this is very similar to photoexcitation of a diene. Dienes, when they are photoexcited, electron density is removed from Psi2 and pushed into Psi3. And similar bond length changes are observed. When you complex a metal, similar bond length changes are observed. Here is a butadiene molecule which is embedded in a cyclic system. So this is cyclohexadiene. Cyclohexadiene also has got a shorter bond between C2 and C3 and a bond lengthening of C1 and C2. So this is reminiscent of what we saw with butadiene and FeCO3. In this molecule which I have pictured for you, it's very clear that all four carbon atoms are not interacting equally with the iron atom. There is a slight change in the bond distance. The terminal atoms are further away from iron. Partly this is due to the fact that there is a CH2 group here and a CH2 group here in the cyclic system, which is repelling the iron. And as a result, the bond distances between C1 and iron are longer than C2 and iron. We will continue our discussion of metal butadiene complexes and metal alkyne complexes in further lectures.